Okay, now let me continue with the second part of this topic. Okay, that is on the chiller sequencing. So what do I mean by chiller sequencing? It means, right, how should your equipments, okay, because in a chiller plant we know we have all these equipments such as the chillers, your primary pumps, secondary pumps, condenser water pumps, and your cooling towers. So which one should start first? Which one should start later? Okay, because when you switch on a chiller plant, when you command it on, not all the equipments will start at the same time. Okay, because the current surge will be too high. So usually we will do it in sequence. Maybe every 5 minutes, the next equipment will start. Okay, then another 5 minutes, the third equipment will start. Okay, then maybe it will take around half an hour before all the equipment start and get stabilized. Okay, so usually when let's say the chiller plant is being command on by either the thumb schedule in the BMS, or let's say you use the BMS to command it on, what will happen? Okay, so first your valve at the condenser water pipe must start to open first. Okay, so let's say you have a chiller. Okay, you have your condenser water loop. Okay, this is your cooling tower. Okay, then you also have your chilled water loop. This is your AHU. Okay, so this one is chilled water loop. Then this one is condenser water. So what happened is, to help you to remember, always the condenser water loop will always start first. Okay, this part must be in operation first before you start the chilled water loop. Okay, so let's say the condenser water loop must kick in first. The valve must be open. Okay, so the valve must be open, and the next thing is your pump. Okay, your condenser water pump will start. Okay, because it's very dangerous if your valve is closed and your pump is on. So you will build up the pressure and your pump may spoil. Okay, so it must ensure that the pipe is, all the valve that is flowing in this condenser pipe must be open first before you start the pump. After you start the pump, you can safely switch on your cooling tower. So your cooling tower fan will start to on. Then your condenser water loop will be in operation. Next, we will go to the chilled water loop. So have to make sure that all your chilled water valve, okay, for example, the chilled water valve must be open. Okay, so once it's confirmed open, your chilled water pump, okay, chilled water pump will command on. Okay, then lastly, the very last equipment, right, will be your chiller. Okay, so the general rule of thumb: condenser water pump first, followed by cooling tower, followed by chilled water pump, and lastly is your chiller. So whenever the previous equipment is not on, the status is not on, the next equipment will not start. Okay, the next equipment will not start. So you may see that, oh, maybe the BMS will start to prompt you that there will be some alarm if something happened along the way. So this whole process may easily take around half an hour, okay, 30 minutes before everything gets stabilized. So what happens if you have more than one chiller? Okay, that means you have more than one set of equipment, you have more than one cooling tower, more than one chilled water pump and condenser water pump. So BMS may do this by using this strategy called the lead and lag sequence. Okay, so the lead equipment will be the first set of equipment to start. So let's say you have chiller 1, chiller 2, chiller 3. So how do we know which chiller should I operate first? Okay, then followed by the next one. So you can use this lead lag sequence. So for example, you have 3 chillers. All the 3 chillers, you have 4 chillers. Let's say you have 3 500-ton chiller, so-called the 3 big chiller, and 1 small chiller, 250 ton. So how can you sequence them? Okay, so for example, if your strategy is having sequence number 1, 2, 3, that means you will always start chiller 1 first. Okay, then if your load is increasing, then you will start the lag chiller, which is chiller 2. Then if it increase further, then you will start the next chiller, which is chiller 3. Okay, and of course this sequence don't have to be fixed. You can run it at 1, 2, 3, 2, 3, 1, or 3, 1, 2. Okay, but how do you determine that? you can try to maybe change every day. Okay, so some buildings they may have this sequence change every day. So let's say Monday is 1 2 3, Tuesday is 2 3 1, Wednesday is 3 1 2. Okay, so what is the advantage of doing this? You will actually make sure that all the chillers, right, will be will run at the same load. Okay, they will have the equal run hours. Okay, so for example, your chiller A is having 500 hours, chiller 2 is 500 hours, chiller 3 is 450 hours. So you should always start to run chiller 3 first to make sure it catch up, and at the end of the day, they should have the equal run hour. Okay, so of course you don't have to do it the daily change, you can do it weekly change or even monthly change. Okay, as long as at the end of the day, the 3 chillers should all have quite equal amount of run hours. That is for better maintenance. Okay, rather than always run the same chiller again and again, then the other 2 chiller have very low run hour, then it's not very healthy. Okay, because chiller 1 may deteriorate faster, then your efficiency may all be messed up. So, for example, what is chiller staging? Okay, so chiller staging, right, is about having a time schedule, okay, to control the start-stop of chillers. So, for example, we know that the peak period always start around 7 AM. Okay, so you will start your chiller 1 at 7. Then you know that during maybe before noon, the load will be very high, so you will start your second chiller, then followed by your third chiller maybe at 2 PM. So this is what we call using time schedule. You have a fixed time to start certain chillers. Okay, so if the cooling load profile changes frequently, then it's not so ideal. This is only ideal if you know that your chiller, as in your load, building load, is always having the same pattern. That means every day 7 AM it will have certain amount of load. At 11 AM usually it will have the load that it will be a certain values and things like that. If it's always very fixed, every day is the same, then it's good to have time schedule to control. If not, it will be better to use chiller staging method. So what do I mean by chiller staging method? Okay, how do we determine when to start or stop a chiller? So basically there are 3 common methods. First, we can base on building cooling load calculation. Okay, if not, we can base on the chilled water return temperature, and the last method is built on the chilled water flow rate. So whichever the method is used, the very first chiller, right, must be always by time schedule. That means 7 AM you must start that chiller. But when to start the second and third chiller, right, it all depends on either one of these, either the cooling load, the return temperature, or the water flow. So let's look at the building cooling load method first. So for cooling load method, okay, the BMS, right, will calculate the building cooling load first using your temperature sensor and flow meter, like what we have learned in topic 2. So if the chiller capacity, for example, is 500 ton, let's say your building cooling load is increasing slowly, like 300 tons, 400 tons, and finally, let's say it hit 90% of this capacity. Let's say 90% of this capacity is 450 tons. So let's say your cooling load start to increase above 450. What will happen? It will kick in the second chiller. Okay, it will start the next chiller. Okay, if not, it will always operate one chiller only. Only until your cooling load is above certain amount, that is 90%, I will start the second chiller. Okay, so that is the 90%. But when should I cut off this chiller? That means when should I switch off one chiller? When it is less than 80% of the combined load. Okay, so when it's less than when it's less than 80% of one chiller. So let's say after that, right, it increased to 500 tons, 600 tons, so the 2 chiller is operating. But let's say your load start to drop, okay, and it drops all the way to 400 tons. That means it's one chiller less, 80% of one chiller. Okay, so let's say it dropped below 400 tons, let's say to 350, then it will cut off one chiller. Okay, so that's the general idea. So let's look at one example, then you will get a better idea. So let's say you have 3 times 500 ton chiller, and the chiller sequence is 1, 2, 3. So describe the chiller staging with reference to a load profile. So let's say your load profile looks something like this. So first, okay, let me show the load profile in one slide first. So let's say your load profile is something like this, okay, and so what happened? Chiller 1, which is the lead chiller, will start at 7 AM. Okay, it will start at 7 AM because of time schedule, which is over here. Okay, so no matter what, okay, every day 7 AM it will start the lead chiller. Okay, so what happened? Your load will start to increase. So it will increase at a certain amount. That means 90% of the chiller capacity. That means when it hit 450 tons, which is over here, when it hit 450 tons, it will start to kick in the second chiller. So this happened at around 8:40 AM. So at 8:40 AM, you will expect your second chiller to kick in because it hit 90% above your chiller capacity. Okay, so for example, let's say your load continue to increase, okay, continue to increase, and let's say it hit 90% of the 2 chillers now. So 90% of 2 chillers is 900 tons. So when it hit 900 tons, which is somewhere over here, okay, it will kick in the third chiller. Okay, and this will happen at around 10:30 AM. So at 8:40, it start the second chiller. At 10:30 AM, it will kick in the third chiller. And this will run for a while. Okay, it will run all the way until your load start to drop below 80% of 2 chiller capacity. Okay, so now 3 chillers are in operation, but let's say it dropped below 80% of 2 chiller capacity, which is 800 tons. One of the chiller will be unloaded. The last chiller that start will first be cut out. Okay, so when it drops below 800 tons, which is over here, at around this time, 5:30 PM, your third chiller will be cut off. Okay, and let's say it continue to drop until it is 80% of 1 chiller capacity, which is 400 tons. That is at this period, it will cut out the second chiller. And that happens at around 7 PM. And finally, your chiller 1 will stop at around 10 PM, and this is because of time schedule. So only the first chiller 1 will start and stop because of time schedule, and chiller 2 and chiller 3 will cut in and cut out because of the load. Okay, so rule of thumb, above 90%, it will cut in the next chiller. Below 80%, it will cut out 1 chiller. Okay, so a summary, you can use this diagram as a summary. So you will notice that how come it is 80% and 90%? Why not above 90% I cut in, but let's say below 90% I cut out? If that is the case, you can imagine that your chiller will keep cutting in and cutting out. Let's say it keeps fluctuating above 450, let's say it's 451 R-ton, you cut in a chiller, but let's say it's 451, you cut in the second chiller, but let's say it dropped to 449, you cut out the chiller. So that will be very, very unhealthy for the chiller. You will be always cutting in and cutting out, which is very damaging for the chillers. So you must make sure there's certain so-called bandwidth, or we call it dead band, okay, such that there's room for it to move, okay, before you decide to cut in or cut out the chiller. Okay, so in this case, we have 10% of allowance. So that is using cooling load. Now the second method is more straightforward. Let's say you are using chilled water return temperature to control the start-stop of the next chiller. Because we know that the design chilled water return temperature is usually at around 12.2 degrees Celsius. So let's say you have a fixed value, 1.5 degrees Celsius. Let's say it's above 1.5 degrees Celsius, you can start the next chiller. So let's say it's at 13.7, let's say your return temperature is getting higher and higher because your load is increasing. Your return temperature will increase accordingly. So let's say your return temperature start to climb up, you will kick in the next chiller. And let's say your return temperature start to drop more and more, that means the building don't require so much cooling now. That's why your return temperature is low, then you cut out 1 chiller. So that is another strategy. This is very straightforward. Okay, that means you use the return temperature to play. So your bandwidth is 3 degrees Celsius. Okay, plus minus 1.5. So your bandwidth is 3 degrees Celsius. Depends on your return temperature. And the last method, okay, so the return temperature at the header, let's say it's 12.7. Okay, so everything is fine. But let's say this value increased to 13.7, then you will cut in the next chiller. Okay, so that's meaning of using return temperature. The last method is using flow, okay, chilled water flow rate. Because we know that when the load is reducing, the valve is closing, usually the pump will also be reduced in speed and your flow rate will drop. So let's say you have a design flow. Let's say your design flow is 40 liters per second. Let's say it dropped below your design flow by 10%. Okay, so let's say now it's flowing by around 36%. Okay, let's say it's 10% above your design flow. Let's say it's 44 liters per second. You cut in the next chiller. Okay, so same thing. Let's say it dropped below a certain percentage. Let's say 10%. You will cut out the chiller. So that is another method you can use, but this is not so common and not so popular because the flow rate may fluctuate quite a bit. So in a nutshell, there's no one perfect method for all buildings. Okay, so it depends on your operation, depends on your design. So some method may be more suitable. Okay, the other method may not be as suitable, but we can always use the different methods to cross-check each other. Okay, to make sure that you have a good controls. You have a very good controls over your chiller staging. And sometimes you may also need to have manual intervention rather than leave it everything automatically. So what are some of the challenges that building owners may face? Okay, so you may notice that chiller staging may not be very, very commonly employed because sometimes the control strategies is quite complex and sometimes you have lack of understanding of the system design. Or let's say the design or if your design or your chiller selection in the first place is not appropriate. So no matter what you do, right, okay, your chiller will always operate at a very inefficient manner. So there's a few challenges you may face, and of course sensors inaccuracies, because all this depends largely on the sensor accuracy, such as your temperature sensor and your flow meter. They must be very accurate to give you very correct load calculation. Okay, so your sensor location may be wrong, or when your building, when it's handed over, okay, it's not fully occupied. So all the control strategies, right, it's not tested when it's full load. So sometimes it may take 2 years or even 3 years for all the buildings to be fully functional and stabilized before you can try out all these control strategies. So these are some of the things that or challenges that you may face. Okay, if you want to use all these chiller staging strategies.